the output is equal to 1 because irrespective of the change in the variable a and b, the output remains 1. So as I have discussed earlier, to minimize this function, we need to make the group of ones. Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we learned about the 2 variable and the 3 variable K-map. So in this video, we will learn about the 4 variable K-map, and we will see that how to minimize the 4 variable boolean function using the K-map. So first of all, let us see the construction of this 4 variable K-map. Let's say these ABCD are the 4 variables of this function, where this A is the MSB and the D is the LSB. So this is one of the way to construct the 4 variable K-map. So here the binary number, the output is equal to 1 because in this case just consider these two ones alone. So the first cell represents A bar Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we learned about the 2 variable and the 3 variable K-map. So in this video, we will learn about the 4 variable K-map, and we will see that how to minimize the 4 variable boolean function using the K-map. So first of all, let us see the construction of this 4 variable K-map. Let's say these ABCD are the 4 variables of this function, where this A is the MSB and the D is the LSB. So this is one of the way to construct the 4 variable K-map. So here the binary number beside each row represents the possible values of the variable A and B, while the binary numbers at the top of each column represents the possible values of the variable C and D. Now for the 4 variables, there are total 16 possibilities. Or in other words, for the 4 variables, there are total 16 minterms, right? So the each cell of the K-map represents the specific combination of the variable A, B, C and D. Now we know that the each combination of the variable A, B, C, D represents the specific minterm. That means here, the each cell of this K-map represents the specific minterm. So here, the number at the top right corner of the each cell represents the specific minterm which is represented by that cell. So now, let us see the arrangement of these cells in the K-map. So here, the numbering beside the each row and the column is done in the gray code form so that the pair of the adjacent cells are only one bit apart. For example, if you go from the minterm 4 to the 5, then only last bit is changing. Similarly, if you go from the minterm M5 to the M13, then only MSB is changing. That means between the pair of the adjacent cells, only one bit is changing. Now the cells in the top row and the bottom row, which are in the same column, are also adjacent to each other. For example, this minterm M1 and the M9 are also adjacent to each other because between them only MSB is changing. Similarly, the cells in the first and the last column in the same row are also adjacent because if we wrap this map, then those cells will be adjacent to each other. For example, this minterm M12 and the M14 are also adjacent to each other because between them only this second bit from the LSB is changing. So because of this Greek code formatting, the cells or the minterms are not in the sequence. That means if you see the numbering of these cells, then after the 1, we have a 3 instead of the 2. And likewise, after 5, we have a 7 instead of the 6. So of course, from the combination of the variables ABCD, we can identify the minterm which is represented by the particular cell. But directly, without looking at the input combinations, if we want to write the minterms and if we want to draw the K-map, then this is how we can do that. So for First of all, write down the possible combinations of the variable a and b beside each row in the gray code form. Similarly, write down the possible combinations of the variable c and d on the top of each column in the gray code form. Now, for the numbering of the each cell, start from the top left corner and write 0, 1, third row, and once again write 8 and 9 from the left to it contains these mean terms. As such, it represents the mean term M9. Similarly, these A for the mapping 3 variable, and if we make the for the case which cannot be grouped with the other mean terms. Similarly, in this case, we can also make the group of mean term 5 and 7. Now we have seen that the two cells at the edges are also adjacent to each other. So here we can also combine these two ones. Similarly, let us see likewise the two ones. Similarly, let us see columns are also adjacent to each other. So we can combine these ones. So now we understood that is this function it if you see, then we can make the group of these four ones which is in the same row. Now once we first of all using the K map. So first of all, we can make the group of this D. Likewise, this one corresponds to A dot B dot C dot D. And similarly, the last one corresponds to A dot B bar dot C bar dot D. Minimize it. So first, let us make the group of these two ones. Similarly, we can also combine these two ones and this group remove these variables is 1, 0 and 1 respectively. Therefore, this group represents A dot C bar dot D. Let us take the couple of more examples. Similarly, we can group only this not. That means while minimizing whenever it is possible, then here instead of making the group of these two ones, we can make the group of four ones. And by making the group of 4, we can reduce the number of variables in that product term. That means while minimizing whenever it is possible, try to make the bigger group of ones so that we can reduce the number of variables in that product term. So now in this group, the variable a and b is not changing and therefore this group represents a bar dot b. Likewise, in the second group, the variable b and c is not changing and therefore this group represents b dot c. And if you see this third group, then in this group, the variable a, c and d is not changing. Therefore, this group corresponds to a dot c bar dot d. And if you see the overall minimized function, then it is the summation of all. Then we can cover the ones in the second group, the group of 4. So out of the three ones, whenever it is possible, just aim for making the larger groups even for covering the single main term. So that we now sometimes during the minimization, the order in which we are making the groups might be wrong. Or sometimes even the selection of the group itself might be wrong. And in such case, perhaps we may not get the minimal expression. So to avoid that, always after making the groups, just check that after the grouping, is there any redundant group or not. And in case if you find any redundant group, then just eliminate that group. Because without using that group also, we can cover all the ones. So let us understand that through one example. So let's say this is the function f6. So first can be covered by making the group of 4 ones. Similarly, the two ones in the second row can also be covered by making the group of 4 ones. Since the first and the last columns are adjacent to each other, so we can make the group of 4 ones. And now if you see, then all the ones in the group gets covered. But if you closely observe, then the first group which we have made is the redundant one. Because just by using these three groups alone, we are able to cover all the ones. Therefore, we can remove that redundant group. So now, this group corresponds to AC. Like Likewise, these Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the don't care conditions in the digital circuits. Now so far in our discussion, the Boolean functions which we have discussed were actually the completely specified functions. That means for such functions, the output is equal to 1 for the certain input combinations, while for the remaining input combinations, the output is equal to 0. Or in other words, for all input combinations, the output is well defined and it is equal to either 0 or 1. But in practice, in some applications, the function is not specified for the certain input combinations. For example, in the 8421 BCD code, these 6 combinations are the unspecified and these 6 codes are the invalid codes. So the output for these combinations could be either 0 or 1. But since they are specified for the certain equal to 0. The Boolean functions which we have discussed were actually the completely specified functions. That means for such functions, the output is equal to 1 for the certain input combinations, while for the remaining input combinations, the output is equal to 0. Or in other words, for all input combinations, the output is well defined and it is equal to either 0 or 1. But in practice, in some applications, the function is not specified for the certain input combinations. For example, in the 8421 BCD code, these 6 combinations are the unspecified and these 6 codes are the invalid codes. So the output for these combinations could be either 0 or 1. But since they are the invalid codes, so we actually don't care what is the output for these combinations. So such input combinations for which the output is unspecified are called the don't care combinations. and they can be used in the K-map for the simplification of the Boolean function. Now, since the output is not specified for these don't care combinations, so in the K-map, these don't care combinations are defined by the symbol X or D. And during the minimization, it can be considered as either 0 or 1. So while we are finding the minimal expression in the sum of product form, then these don't care terms can be considered as 1. And similarly, when we are finding the minimal expression in the product of sum form, then these don't care conditions can be considered as 0. So depending on our conveniency, we can treat these don't care terms as either 0 or 1. So let us take few examples so that it will get clear to you. So let's say, so the usage of this don't care term is optional. But using the don't care terms, if we are finding the further simplification of the Boolean function, then we should use these don't care terms. So first of all, let us find the response to b bar dot c. So without using the don't cares, if we see the minimized function, then that is equal to a bar dot b bar plus a ones. Similarly, using the don't care min term m4, we can make the group of these four ones. So in this way, a bar ones. So this group corresponds to b bar, while this group in the yellow color corresponds to a bar. And if we see the overall minimized function, then that is equal to a bar plus b bar. So in this way, using the don't care terms, we can further simplify the Boolean expression. So let us take a couple of more examples. So finding the minimum, we so let us take few examples. So minimal solution, because in this group, in this case, using the don't care terms, we can further simplify. simplify the is equal to a bar plus b bar. So in this way, using the don't care terms, we can further simplify the Boolean expression. So let us take a couple of more examples. So this function f2 is the function of 4 variables. And here, but suppose if we want the minimal solution in the POS form minimization in the Z. First of all, let us mark the remaining cells in the K-map with. We can treat these don't care terms as 0. So let's say for the same Boolean function, we want to find the minimal solution in the POS C. In the blue color, minimized function. Then it is the summation C bar dot D bar, while this group corresponds to B bar dot C. That means this function f2 dash is the summation of this B bar dot C and the C bar dot D bar. And the function f2 is the complement of the f2 dash. So using the De Morgan's law, we can say that this f2 is equal to B plus C bar dot C plus D. So that is the minimal expression in the POS form. So in this way, even if the function is given to us in the sum of product form, then also we can find the minimal solution in the POS form. And during the minimization, we can treat these don't care terms as 0. So of course, in this case, there was no need to use the don't care terms, but in general, if required, then these don't care terms can be used during the minimization. So let us take another example. So in this third example, this function f3 is given in the POS form. So first of all, let us represent this function in the K-map. And first, let us represent. So during the minimization, we should cover all the one scalar dot terms. We can further say corresponds to B dot C. And if you see the overall minimized function, this don't these two groups product form. Then also we can now let us represent this don't care terms with the x. So here during the minimization in the POS form, we can consider all these don't care terms as 0. So as you can see, here we can make the group of these 4 zeros and these 4 zeros. And using the don't care max term m2, we can make the group of these 4 zeros. So now all the zeros in the map gets covered. So this group in the blue color corresponds to C dot D, while this group in the pink color corresponds to B bar dot D bar. And likewise, this last group corresponds to A dot B bar. So here, since all the groups are the groups of zeros, we can make the group of.
In this class, we are going to discuss about rules for simplification of K-map. So here in last class, we discussed that by using K-map, we can solve Boolean expressions easily without using Boolean laws, and unit is called as quarter. So another one is octet. So octet means we can group 8 ones. So like that, in similar way we can group 2 power n cells, that means all 2 multiplication, that means we can group 16 ones in given K-map. If you are having ones like this, then you can group a double. So that means you can group like this. So the value of this prime implicant is the given this first exams. All 2 multiplication, that means we can group 16 ones, 32 ones.
Can be represented. So as you can see, this product of sum form contains all the cells.
In this presentation, landing any way you want to, because you have to signal it. So your legs are like don't care. So we will see how to use this don't care along with this compulsory conditions or the min terms, which is 0 0 you would have made in case you were don't having the don't cares. Then the other group, the other pair you can say is this one, or it could be 0 as well, as it is don't care. We can take it as 1, we can take it as 0, whatever you want to, but we take it as 1 in case we have to reduce our K map by using the min terms, and we take it as 0 in case we have to reduce our K map or reduce our function by using the max term. So keep this thing in your mind. This is when you are operating with min terms, and this is when you are operating with max term. Because what we want out of the K map, we want the greatest possible group of the ones which are 2, 4, 8, 16 and so on, and we want it to be the largest. We have learned already about the prime implicants. Okay, implicant is the group of 1, prime is the largest group of 1. So we wanted the largest. So what if I change this cross with 1? So let's do it here. Let me make the another map for you. This is A, B, C. So this was your 1. I'm just writing this again in this map, but in this map I'm going to change this cross by 1. Why? Because this is the don't care and I can take it as 0 or 1. And now in this particular example I'm minimizing my function f by using the k-map, and in that k-map I'm using the minterms, and I have already explained you that in case of minterms we are going to take the don't care as 1. So I took the don't care as 1. Now let's do the pairing, or let's make the combinations or group of ones again. Now I'm not going to combine these two ones in this way like I did here, but I'm going to combine it like this way. Now it's not a pair, we have just made it a quad. Okay, the group of 4 ones. Similarly, I am not going to combine these two ones like this way, but I will do it in this way. So instead of having the pairs, the two pairs, I'm having the two quads. Okay, this is your quad 1, this is your quad 2, and as I have told you, when you do the pairing, when you are having the group of 2 ones, you eliminate the one variable. When you are having the group of 4 ones, you eliminate the 2 variable, and so on. So in this case you are having something like, from this you would have either AB, BC or CA in complemented or a normal form, but now you are having the only single literal odd with the other one. Let's see how. For example, first let me write the function from this k-map. In this we are having a bar, and the C is changing from 1 to 0, so C is neglected, and B is written as B because it is 1. Now or A, and B is 0, so it's changing from 0 to 1, so B bar. So A bar B or AB bar, this is actually your A XOR B. So you can see that this thing, and now I'm going to write the function from this k-map. So this is 0 1 0 0 0 1 1 1 1 0. So let's write it for the quad 1. In this A is changing, you can see this quad 1, in this A is changing from 0 to 1, but your B is not changing, it is 1, and C is changing from 1 to 0. So wow, we have just A reduced and also the C is eliminated. We just made A and C as 1, so we are left with B. Okay, if you don't know the basic of the k-map, then you may refer my earlier lectures on this k-map series, so don't get confused here. It's a very basic thing, we have actually moved on these things. So this don't care is actually the last part that you have to study in the k-map. So we are going to reduce this, write this quad 2. In this quad 2 you can see that B and C both are changing from 0 to 1, so they are 1, and A is 1 and it's not changing, so I will write it as A. So you can see that the same function can be written as A XOR B, which is A complement B or AB complement. In this you can see extra literal in every what you can say, in every ANDed operation, but here you are having A or B, only a single OR gate is required, but here AND AND gate is required, then another AND gate is required, and then OR gate is required. So 3 gates are required, but here only single 2 input OR gate is required. So this is the advantage of using the don't care as 1 in case of min terms grouping, and 0 in case of max term groupings. So I think it is now clear to you what the don't care is and how we have to use. Welcome to this. In this presentation you are having something like, from this you would have. Welcome to this presentation in which I will try to clear the doubt of Rodolfo Lozano. The first function is A exclusive or B. Okay, the second function is equal to most of. We are having in this presentation,
then that is equal to A bar plus B bar. So in this way, using the don't care terms, we can further simplify the Boolean expression. So let us take a couple of more examples. So this function f
ஹலோ ஃப்ரெண்ட்ஸ், இன்றைக்கி நாம் 4 வேரியபிள் கேம் அப் வித் டோன்ட் கேர் கண்டிஷன் பற்றி பார்க்க போகிறோம். கொடுத்துருக்கிற ப்ராப்ளம், ஃபைண்ட் த ரெடியூஸ்ட் எஸ்ஓபி ஃபார்ம் ஆஃப் த ஃபாலோயிங் ஃபங்க்ஷன் எஃப் ஆஃப் ஏபிசிடி இஸ் ஈக்குவல் டு சமேஷன் எம் ஆஃப் 1 3 7 11 15 ப்ளஸ் சமேஷன் டி ஆஃப் 0 to 4. ஸோ இங்கே கொடுத்துருக்கிற ப்ராப்ளம் எஸ்ஓபி ஃபார்மேட்டில் கேட்டிருந்தாங்க அப்படின்னா பைஎம் கொடுத்துருக்காங்களான்னு பாருங்கள். பைஎம் கொடுத்துருந்தாங்கன்னா அது வந்து பிஓஎஸ் ஃபார்மேட், அது எஸ்ஓபி ஃபார்மேட்டாக கன்வெர்ட் பண்ணணும். நமக்கு ப்ராப்ளம் டைரெக்டாக கொடுத்துருக்காங்க, அதனால் பிரச்சனை இல்லை. சம்டைம்ஸ் கேபிட்டல் M0, கேபிட்டல் M1, கேபிட்டல் M2 அந்த மாதிரி வேல்யூஸ் கொடுத்துருந்தாங்கன்னாவும் அது பிஓஎஸ் ஃபார்மேட், அது வந்து எஸ்ஓபி ஃபார்மேட்டாக நம்ம ஃபஸ்ட்டு கன்வெர்ட் பண்ணணும். இந்த சமேஷன் டிக்கு பதில் சம்டைம்ஸ் சமேஷன் பைன்னு கொடுப்பாங்க, இல்லைன்னா பை எம் ஆஃப் அந்த மாதிரி கொடுப்பாங்க. ஸோ சமேஷன் கொடுக்காம டி மட்டும் கொடுப்பாங்க. அப்படி கொடுத்தாலும் அது டோன்ட் கேர் கண்டிஷன் தான். ஸோ இப்போ ஃபஸ்ட்டு நம்ம சால்வ் பண்ண போகிறோம். நமக்கு ஏற்கனவே தெரியும் ஏபிசிடின்றது 4 வேரியபிள், அதனால 2n ஃபார்முலாவில் 2 is equal to 16 செல்ஸ் மேக் பண்ணிக்கிறோம். இங்கே என்ன ஆல்பபெட்ஸ் கொடுத்துருக்காங்க, அந்த ஆல்பபெட்ஸ் எடுத்துக்கிறோம். இங்கே ஏபிசிடின்றதுனால இங்கே ஏபி, இந்த சைடில் சிடி. இந்த பேசிக் ஸ்ட்ரக்சரில் நமக்கு ஏற்கனவே தெரியும். கண்டிஷன் இங்கே கொடுத்துருக்கிற ப்ராப்ளம் 0 to 4, அந்த 0 to 4ல் மட்டும் எக்ஸ்ன்னு ரெப்ரசென்ட் பண்ணுறோம். அதே போல் டோன்ட் கேர் கண்டிஷனுக்கு எக்ஸை ரெப்ரசென்ட் பண்ணி கொடுத்துருக்கிற ப்ராப்ளமில் நமக்கு 4 1s இந்த காம்பினேஷனில் நமக்கு கிடைக்குது. ஸோ இது வந்து 4 கன்சிடர் பண்ணால் எனக்கு 4 1s வரும். நம்மளோட எய்ம் 1-ஐ வந்து குரூப் பண்ணணும், எந்த ஒரு ஒன்றுமே தனியாக இருக்கக்கூடாது. அது சைடில் என்னெல்லாம் இருக்குதுன்னு பாருங்கள், எல்லாமே வருது. ஸோ இது ரெண்டுத்தையும் எடுத்தீங்க அப்படின்னா பி ப்ளஸ் பி பார் இஸ் ஈக்குவல் டு 1 கண்டிஷனில் ஏ பார் மட்டும் காமனாக இருக்கும். இதுலேயும் திரும்பவும் பி ப்ளஸ் பி பார் இஸ் ஈக்குவல் டு 1 காம்பினேஷனில் இல் கெட் இல்லை ஏ பார் மட்டும் கிடைக்கும். ஸோ இந்த ஏ பாரும் ஏவும் அகெயின் ஏ ப்ளஸ் ஏ பார் இஸ் ஈக்குவல் டு 1 காம்பினேஷனில் கேன்சல் ஆகிடும். ஸோ ஏபி சைடில் எல்லாமே கேன்சல் ஆகிடும். பட் சிடி சைடில் நமக்கு 1 1 இருக்குது. இந்த 1 1 எதை ரெப்ரசன்ட் பண்ணோம், சி அண்ட் டிஏ. ஸோ குரூப் 1ஓட வேல்யூ சிடி. அதே போல் குரூப் 2 எடுத்துக்கிட்டிங்க அப்படின்னா ஏபி சைடில் 0 0 மட்டும் வருது. ஸோ 0 0 அப்படியே வந்துடும். 0வை எப்படி ரெப்ரசன்ட் பண்ணலாம், ஏ பார், இந்த 0வை பி பார்னு கன்சிடர் பண்ணால் எனக்கு 4 நமக்கு கிடைக்குது. ஆஃப் ஒன்ஸ் வந்து 16 நெய்பரிங் ஒன்ஸ் இருக்கான்னு செக் பண்ணணும். ஏன்னா இது மேக்ஸிமம் 16 செல்ஸ். 16 செல்ஸில் நம்பர் ஆஃப் ஒன்ஸ் இல்லை அப்படின்னா அடுத்த ஆப்ஷன் 8 நம்பர் ஆஃப் ஒன்ஸ். 8 நம்பர் ஆஃப் ஒன்ஸும் இல்லை அப்படின்னா தான் 4 ஒன்ஸ். 4 ஒன்ஸும் இல்லைன்னா 2 ஒன்ஸ். 2 ஒன்ஸும் பாசிபிலிட்டி இல்லைன்னா சிங்கிள் குரூப்பிங். இப்போ நமக்கு கொடுத்துருக்கிற ப்ராப்ளமில் நமக்கு 4 ஒன்ஸ் இந்த காம்பினேஷனில் நமக்கு கிடைக்குது. ஸோ இது வந்து 4 சேர்த்து ஒரு குரூப்புன்னு எடுத்துக்கிறோம். இப்போ பார்த்தீங்கன்னா இந்த 1 மட்டும் தனியாக நிற்குது. இந்த 1-ஐ மற்ற நெய்பரிங் 1ஓட கம்பைன் பண்ணும்போது மேக்ஸிமம் நம்பர் ஆஃப் ஒன்ஸ் இவ்வளோ பாசிபிலிட்டி இருக்கோ அதை குரூப் பண்ணணும். இப்போ இந்த 1-ஐ பக்கத்தில் இருக்கிற 1ஓட கம்பைன் பண்ணனா எனக்கு 2 குரூப்பிங்ஸ் தான் வரும். பட் இந்த எக்ஸை நான் வந்து 1ன்னு கன்சிடர் பண்ணால் எனக்கு 4 ஒன்ஸ் வரும். ஸோ இப்போ தெரியும் டோன்ட் கேர் கண்டிஷன் எதுக்கு யூஸ் ஆகுதுன்னு. இப்போ இந்த எக்ஸை வந்து நான் ஒன்னு கன்சிடர் பண்ணுறேன், அதே போல் இங்கே இருக்கிற எக்ஸை ஒன்னு கன்சிடர் பண்ணுறேன் அப்படின்னா இந்த நாலத்தையும் சேர்த்து ஒரு குரூப்பாக நம்ம ஃபார்ம் பண்ணிக்கலாம். ஸோ நம்மளோட எய்ம் ஒன்னை வந்து குரூப் பண்ணணும். எந்த ஒரு ஒன்றுமே தனியாக இருக்கக்கூடாது. அது மேக்ஸிமம் நம்பர் ஆஃப் வேல்யூஸ் ஒன் ஃபார்ம் ஆகிற மாதிரி வரணும். அதுவும் நம்மளோட கண்டிஷன்ஸ் 16 ஒன்ஸ், 8 ஒன்ஸ், 4 ஒன்ஸ், 2 ஒன்ஸ் அந்த காம்பினேஷனில் தான் இருக்கணும். ஸோ இதை வந்து G2ன்னு எடுத்துக்கணும். நமக்கு ஏற்கனவே தெரியும் G1 குரூப்பிங் எப்படி எழுதணுன்ட்டு. G1 எப்படி எழுதுனாலும் ஏபி சைடில் என்னெல்லாம் இருக்குதுன்னு பாருங்கள், எல்லாமே வருது. ஸோ இது ரெண்டுத்தையும் எடுத்தீங்க அப்படின்னா b plus b bar is equal to 1 கண்டிஷனில் a bar மட்டும் காமனாக இருக்கும். இதுலேயும் திரும்பவும் b plus b bar is equal to 1 காம்பினேஷனில் you'll get
plus C plus D. I want to implement
In this presentation, we are going to study Quine-McCluskey minimization technique, also called as tabular method. For many applications, the number of inputs is too large, so the simplification using K-maps becomes too difficult. This happens when the number of variables is greater than 6. You already know two methods for minimization. The first one is Boolean algebra, second one is K-map, and third one we are going to study in this presentation called as tabular method. K-maps are good. You can use K-maps for 3-4 variable minimization, 5 variables also. And when you have 2 or 3 variables, you can use Boolean algebra. But when you have more variables, it will be very difficult to use K-map as well as Boolean algebra. So we have this method when the number of variables are greater. This technique is based on automatic or computer driven simplification routine. We can use this technique for designing very complex digital systems. We need to brush up two important terms, prime implicant and essential prime implicant, before moving to our tabular method. So first term is prime implicant and second term is essential prime implicant. We have already studied about implicants in K-map lecture, so I'm going to cover this quickly. Implicant is nothing but the group of ones, and prime implicant is the largest possible group of ones. Essential prime implicant is the prime implicant having at least one minterm that cannot be combined in any other way. So this is all that you should know about prime implicant and essential prime implicant. Is too large, so the simplification. In this presentation, we are going to study Quine-McCluskey minimization technique, also called as tabular method. For many applications, the number of inputs is too large, so the simplification using K-maps becomes too difficult. This happens when the number of variables is greater than 6. You already know two methods for minimization. The first one is Boolean algebra, second one is K-map, and third one we are going to study in this presentation called as tabular method. K-maps are good. You can use K-maps for 3-4 variable minimization, 5 variables also. In this presentation, we are going to study Quine-McCluskey minimization technique, also called as tabular method. For many applications, the number of inputs is too large, so the simplification using K-maps becomes too difficult. This happens when the number of variables is greater than 6. You already know two methods for minimization. The first one is Boolean algebra, second one is K-map, and third one we are going to study in this presentation called as tabular method. K-maps are good. You can use K-maps for 3-4 variable minimization, 5 variables also. And when you have 2 or 3 variables, you can use Boolean algebra. But when you have more variables, it will be very difficult to use K-map as well as Boolean algebra. So we have this method when the number of variables are greater. This technique is based on automatic or computer driven simplification routine. We can use this technique for designing automatic or when the number of to use K-map algebra. But when you have more variables, it will be very difficult to use K-map as well as Boolean algebra. So we have this method when the number of variables are greater. This technique is based on automatic or computer driven simplification routine. This technique is based on automatic or computer driven simplification routine. Can use this technique is based on automatic or computer driven simplification routine. We can use this technique for designing very complex digital systems. We need to brush up two important terms, prime implicant and essential prime implicant, before moving to our tabular method. So first term is prime implicant and second term is essential prime implicant. We have already studied about implicants in K-map lecture, so I'm going to cover this quickly. Implicant is nothing but the group of ones. And prime implicant is the largest possible group of ones. Essential prime implicant is the prime implicant having at least one min term that cannot be combined in any other way. So this is all that you should know about prime implicant and essential prime implicant before moving to the tabular method. We will take one example to understand all the steps involved in the tabular method. Example, and let's say the function is y with variables a, b, C and D. A is MSB, the most significant bit, D is LSB, the least significant bit, and the min terms are 0, 1, 3, 7, 8, 9, 11 and 15. So these are the min terms, and we have the function y with 4 variables. Now I am taking 4 variables to explain you the tabular method. However, it was good to use K-map to solve this problem, but I don't want complexity. This is the first problem in tabular method, and I want to avoid the complexity. I want to keep this lecture as simple as possible. Once you understand all the steps involved, you can easily solve the problem with 5 variables or 6 variables. So we will take this example, and at the end of this presentation, once we have the minimized function by using the tabular method, we are going to verify by solving it with K-map. So let's move to the step number 1. Before that, I will write down the binary equivalent for this min terms. I hope you already know these things. No need to write down in your exam, but for reference, I'm going to write down the binary equivalent of 0 is 0, 0, 0, 0. We are having, for first group, we are going to have the min term with no 1. It means 0 is going to be in the first group. In second group, we are going to have the min terms with single 1. So you can see 1 is having single 1, and 8 is having single 1. So 1 and 8 are going to be in group number 2. In the same way, we have to make the group for the min terms having 2 ones, 3 ones, and so on. So this is what we are going to do in step number 1. We will make the table with 3 columns. So let's do it quickly. This is first column. Would be 0, 0, 0, 0. 1 is 0, 2 ones. 7 is having 3 ones, and 11 depending upon this table that we will see shortly. So let's make the table quickly. Nth group with n plus 1th group. If 0 in tabular method, will have the first column is for group, third column is again for binary representation A, B, C and D. Now the second column will have the matched pairs. Now what is this matched pair? This is a new term and very important in tabular method. The matched pair we obtain when we compare the nth group with n plus 1th group. If 0 is the group, then 0 plus 1 is 1, and we have to compare the group number 0 with group number 1 and we will obtain the matched pairs. So a matched pair is the pair we obtain when we compare the nth group with n plus 1th group. If 0 is the group, then 0 plus 1 is 1, and we have to compare the group number 0 with group number 1 and we will obtain the matched pairs. So a matched pair is nothing but it is a pair of minterms which only differ by one variable. Very simple. If we compare the minterms of the group number 0 with the minterms of group number 1, for instance, let's say I'm comparing M0 with M1, then it is a matched pair only if there is a difference of one variable. So let's see, A, B, C are 0 in case of M0 and also they are 0 in case of M1, but D is 0 for M0 and it is 1 for M1. So we can say only one variable is changing, hence M0 M1 is a matched pair, and we have to identify the matched pair from this table and we have to fill the matched pair in step number 2. So this is what we have to do in step number 2 in this table number 2. So group number 0 will have all the matched pairs when we compare the group number 0 with group number 1. In the same way, the group number 1 will have all the matched pairs when we compare group number 1 with group number 2, and so on. You will get a clear view once we will start filling this table. I have already compared M0, M1, and this is our matched pair. So M0 M1 is matched pair, and A is 0, B is 0, C is 0. Now what about D? For D we are not going to write 0 or 1, but we will write underscore. This shows that D is eliminated. Now we will compare M0 with M8 because we have to compare each and every minterm of nth group with the minterm of n plus 1th group, and when we compare M0 with M8 we can see B, C, D are 0 but A is 0 and 1. So this is again the matched pair. So M0 M8 is our matched pair, and we have underscore 0 0 0. Right. One very important thing that you have to keep in your mind, so on. You will get a clear view once we will start filling this table. I have already compared M0 M1, and this is our matched pair. So M0 M1 is matched pair, and A is 0, B is 0, C is 0. Now what about D? For D we are not going to write 0 or 1, but we will write underscore. This shows that D is eliminated. Now we will compare M0 with M8 because we have to compare each and every minterm of nth group with the min term of n plus 1th group. And when we compare m0 with m8, we can see b, c, d are 0 is when you have the min terms in matched pair, and we have underscore 0 0 0. Explain why we are putting this tick mark in front of min terms shortly. Let's move to group number 1. I will compare m1 with m3, and we can see that only one variable is changing. m1 is 0 0 0 1, m3 is 0 0 1 1. Only c variable is changing. So m1 m3 is matched pair, and we have 0 0 underscore 1. I will compare m1 with m9, and let's see what we have. 0 0 0 1 1 0 0 1. Again we have only one variable changing, so m1 m9 is also our matched pair, and we have underscore 0 0 or 1. In the same way, we are going to compare m8 with m3, m8 with m9. I'm not going to do this. Fill this table by yourself, and then we will move to step number 3. I hope you have the same table in your notebook, and don't forget Forget to put the tick mark in front of the min terms that are involved in the matched pairs. So this is step number 2, and now we can move to step number 3. In step number 3 we are going to use this table, and we have to follow the same steps. We have to compare M0 M1 with M1 M3. In the same way we have to compare M0 M8 with M1 M3 and so on, and we have to again check for the matched pairs. So in step number 3 we are going to do the same thing that we have done in step number 2. We will make the table, and we will find out the matched pairs. So let's make the table quickly. Matched E and D. We will compare M0 M1 with M1 M3. M0 M1 is 0 0 0 underscore. M1 M3 is 0 0 underscore 1. So you can see that we have two variables changing, underscore 1 0 underscore. So M0 M1 M1 M3 is not a matched pair. Now this is not a matched pair. We will compare M0 M1 with M1 M9. So let's do it quickly. 0 0 0 underscore, and M1 M9 is underscore 0 0 1. Again you can see we have two variables changing, so it is not a matched pair. In your rough space, do it the way I am doing to avoid the mistakes. This is the method in which most of the people commit mistake. So this is again not the matched pair. We will compare M0 M1 with M8 M9. So 0 0 0 underscore. M8 M9 is 1 0 0 underscore, and you can see we have only one variable changing, that is A. The rest of the variables are same. So in group 0 we have M0 M1 M8 M9 as our matched pair, and the representation is going to be underscore. This 0 1 will be written as underscore 0 0 underscore. In the same way you have to complete this table. I hope your table is same as this one, and don't forget to put tick mark. All the matched pairs are involved, so I will put tick mark in front of all these matched pairs. In step number 4, we have to repeat the same procedure. We will compare group number 0 with group number 1 and group number 1 with group number 2, and we'll write down the matched pairs. But you will find that there is no matched pair after step number 3, and thus we don't need to put a tick mark in front of this matched pairs, and we will write the values for them. B complement, C complement, A is eliminated, D is eliminated, so B complement, C complement. In this we have B complement D, and for this we have C. D. This is our prime implicant. All these three are prime implicant, and we have to also check for the step number 2 if there is any matched pair which is untick, but there is tick in front of all the matched pairs, so they are not prime implicant. In the same way, we have to check for table number 1 and all the min terms have tick in front of them, so they are also not the prime implicant. So we have prime implicants B complement, C complement, B complement D, C, D. 3 are prime implicant, and we have to also check for the step number 2 if there is any matched pair which is untick, but there is tick in front of all the matched pairs, so they are not prime implicant. In the same way, we have to check for table number number 1 and all the min terms have tick in front of them, so they are also not the prime implicant. So we have prime implicants b complement c complement b complement d c d. Now we have to make another table, and we will call this table prime implicant table. So we are going to make the next table, and this is our prime implicant table. Okay, we need more space for this prime implicant table. In the first column we are going to have the prime implicants. They are b complement c complement b complement d c d. We are making this table to find out the essential prime implicant. These three are the prime implicants but not essential, and the minimized function will only have the essential prime implicants. So this table will help us to get the essential prime implicants. First column will have the prime implicants, second column will have the min terms involved, will have the min terms involved. In b complement c complement, you can see we have m0, m1, m8 and m9. m0, m1, m8, m9. So we are going to write it down 0, 1, 8 and 9. In the same way, for b complement d, we have 1, 3, 9, 11. 1, 3, 9, 11. For CD, we have 3, 7, 11, 15. 3, 7, 11, 15. And also we have to write down the given min terms. If you see the problem, and you will find out the given min terms 0, 1, 3, 7, 8, 9, 11, 15. We have to write down this in the last column 0, 1, 3, 7, 8, 9, 11 and 15. We will put a cross in each row under the min terms contained in particular prime implicant. In this prime implicant we have 0, 1, 8, 9, so we will put a cross under 0, 1, 8 and 9. In the same way we will put a cross under 1, 3, 9 and 11, 3, 7 we have 11 and 15. I will make the columns so that I can separate them more clearly. This one is the column having column. Also we have two cross which is alone in the column, like this one. In this column we have two cross, in this column also we have two cross, but in this column we have only one cross. And this is also the column having the single cross, and this one is the column having the single cross. Now we will consider the prime implicants corresponding to this circle. For this 2 we have b complement c complement, so function y is equal to b complement c complement, or corresponding to this 2 we have cd. So this is our answer, and you can see we have eliminated b complement d because this is not essential prime implicant, and we can prove it with the help of K-map. If I draw a 4 variable K-map, we are going to have 16 cells. Okay, this is our 4 variable K-map, the prime implicant. Twelve is zero, 13 is 1, 1, 0, 1, 0, 0, 0, 1. We have 8 and 9, so 8, 9, 10 is 0, 11 is there, 12 is 0, 13 is 0, 14 is 0 and 15 is 1. So this is what we have, and this is our b complement, and this will give us b complement d, and this is absolutely a redundant thing to do because this 4 ones are already combined in first and second group of ones, so no need to combine this 2 plus 2 4 ones again. So b complement d is prime implicant but not essential prime implicant. So this is all for this presentation. In the next presentation we will see tabular method with don't cares. So see you in the next one. 0, 0. underscore. M8 M9 is 1 0 0 underscore, and you can see we have only one variable changing, that is a. The rest of the variables are same. So in group 0 we have M0 M1 M8 M9 as our matched pair, and the representation is going to be underscore. This 01 will be written as underscore 00 underscore. In the same way you have to complete this table. I hope your table is same as this one, and don't forget to put tick mark. All the matched pairs are involved, so I will put tick mark in front of all these matched pairs. In step number 4 we have to repeat the same procedure. We will compare group number 0 with group number 1 and group number 1 with group number 2, and we'll write down the matched pairs. But you will find that there is no matched pair after step number 3, and thus we don't need to put a tick mark in front of this matched pairs, and we will write the values for them. B complement, C complement, A is eliminated, D is eliminated, so B complement, C complement. In this we have B complement D, and for this we have C D. This is our prime implicant. All these three are prime implicant, and we have to also check for the step number 2 if there is any matched pair which is untick, but there is tick in front of all the matched pairs, so they are not.